Hello and welcome to my presentation. This accompanies a thesis that I wrote for the Collège des études osteopathiques, but I wanted to record it in this form because I found the presentation a lot more easy to understand and more direct. So, like this image, the document was quite dense and had a lot of information. And the question is, can you tell easily, not knowing anything about my presentation, can you tell easily that one of these are the ventricles and one of these are the brain tissue or parenchyma? You'll see over on the left, they look very, very similar. And as time progresses through the life of the embryo, it becomes more differentiated. And that's my plan, to help bring people's knowledge of this subject from the undifferentiated mesenchyme of unknowing to a clearer state of knowledge where things are easier to differentiate. The name of the thesis was Motility and Fluctuation, Qualitative Analysis of Form and Fulcra of the Embryonic Brain and Ventricles. This process was very much aided by Julien Fetisson, PhD, DO, who was my thesis advisor. So, just to give a little bit of background on where I'm coming from, why I did this thesis. It started because I had a strong interest in embryology from the beginning of my osteopathic schooling. It's a huge question. How do you get something out of nothing? Usually we're looking at the outside world and things are moving around, they're bouncing, the ball is bouncing off of the ground, but you know, how do you go from a state of, it's really undifferentiated, that's just kind of very chaotic, to a differentiation of two things that you can tell apart and that, you know, work with each other, next to each other. So that was a big inspiration. The other part of the inspiration was how I was seeing embryology talked about in general. Both embryology as a whole, but also even in osteopathy. It's kind of turned into a scapegoat that if we don't know how two things are connected and we're trying to find a connection, we say, oh, it's embryologically connected. And to me, this doesn't make a lot of rigorous sense because, of course, everything is connected embryologically because we start as one cell. So saying that these two things are connected embryologically is just like saying these two things are connected because they both exist. So I wanted to get more precise. The other reason is because I really enjoyed the work of Sutherland. When I was reading Sutherland and I was reading the kind of current scientific literature, I saw really amazing parallels to new scientific research on CSF and what Sutherland was finding. So it really piqued my interest. In specifically, the movement of the pineal gland. Sutherland talks about this movement of the pineal gland that he had sensed with his hands, and he says it flips up and it flips down. And for a while I was just like, okay, well, who knows what he was feeling, if it was kind of accurate from a more scientific standard, or if it was a way he was just interacting with the body and a feeling he had. But when I was looking at some of the CSF research, it actually did show two phases of the CSF, and there was always a point at the pineal gland, and then you would see during one it was pointing down, and one it was pointing kind of up like this. And I found that very interesting because it really matched all the other parameters that Sutherland was talking about. So that was another inspiration for me. Luckily, I came across some MRIs from a guy, a PhD named Bradley Smith, University of Michigan, and he very kindly let me use them. I took the data, I made 3D models going through every slice of the MRIs. Then I printed those 3D models and I kind of hung out with them. They make great bath toys. Good to get them in their natural habitat of water. And then I compared them to what Sutherland's writings were. So, William Gardner Sutherland, D.O., was the founder of the cranial concept, which he always stated was the extension of osteopathy as taught by Andrew Taylor Still. There were 5 elements of the primary respiratory mechanism, which he described, and one of those was motility of the central nervous system. Now, first we have to look at the motility basics. 1, what is motility and what is mobility? Sutherland would state that motility, in his original concept, was when something moved from itself. So, for instance, the central nervous system was said to have motility because it moved without this force that's pushing it around, as opposed to the cranial bones, which were said to possess mobility because they were pushed around, moved by the central nervous system, among other things. Now, in this presentation, or in this thesis, motility was used whenever describing how something moved by itself, as opposed to fluctuation, which was used when describing when things were moving into what phase. So there are 2 phases in the primary respiratory mechanism, one of inhalation and one of exhalation. And there are different movements associated with each movement. Later, we'll talk a little bit more about images that were used to describe movement, but the overall idea was that during inhalation, when looking at the neural tube as a whole, there is a transverse increase, we see right here, and a longitudinal decrease, so a shortening of the long axis of the nervous system. During exhalation, there's a transverse decrease and a longitudinal increase. The element of primary respiratory mechanism, often cited as the primary concept by Sutherland, is that of the fluctuation of the cerebrospinal fluid and its potency. Now the question arises, what is fluctuation anyways? Now it's the transfer of energy through a medium, not the transfer of the medium itself, which would be flow. So this is similar to a wave in the ocean where the molecules don't move horizontally. They move up and down or in little circles, but the energy still gets passed through things, or any sort of wave that comes from something like an earthquake. It's not that the rock travels 50 miles. It's that the rock pushes another rock, which pushes another rock in different ways. This is fluctuation of a wave. Now here we have a quote from Roland Becker. That's still a small point between inhalation and exhalation. The fulcrum, you call it. Easy to know the top and the bottom of a wave, but the midway point is something else. So he talks about a couple of things here. He talks about the top and the bottom of the wave. And what you will notice is that when you have a wave, you never have a peak without a trough, or a trough without a peak. The other thing he talks about is the fulcrum. Now the fulcrum is used quite physically in this presentation, and it's about where things rotate around. So things are always coming back and through this center point, which I will use the fulcrum to describe. Now fluctuation was used whenever I was discussing the interplay between the 2 phases, both in the ventricles and in the parenchyma, or the brain tissue. Now Sutherland often talked about embryology when describing motility of the neural tube. And one embryology especially suited for osteopathy is the biodynamic model from Eric Bledschmidt. This model focuses more on the effect of the physical forces and the flow of fluids in the differentiation of the embryo, as opposed to more chemical aspects, which he said exist and accepted, but thought that this other part was lacking in research. Now he made his discoveries by modeling the embryos. He used slices, I used MRIs, and then he reproduced them in plastic, the whole embryos in different sorts of configuration of organs, I only used the nervous tissue because that was what was accessible to me, and then I 3D printed them where he had people make them in plastic. So this was a big inspiration. Now, three concepts important to Blechschmidt were used in this thesis. First is observing of landmarks. When anything moves, you need to know what it's moving in relation to. Otherwise, you're lost in space. So the difference between a tree growing up and growing away from the soil is very different than the lengthening that happens when there's a line at the movie theater, and although the front of the line, or the top of the tree, is at the door, it moves backwards. And this is an important concept that has to be remembered. Second is that of restraining functions. And I use this in a similar way to the fulcrum, the idea of the fulcrum. And I use this because when something restrains something else, then something has to move around it. So if there's a more fixed point and something's moving away from that fixed point, it might spiral, it might go back the way it came, it might swing around, just like something moving around a point in space. The third concept was the concept of growth movements. Now, Blechschmidt postulated that changes in the morphology of the embryo creates the patterns that dictate postnatal movements and functions. So if the postnatal movements are coded in the growth, and if there's a motility of the central nervous system that moves, then the movements that are postulated in the movement of the central nervous system should be able to be seen in the growth of the embryo. So then we come to the research questions. First one is, using Blechschmidt's biodynamic model, what growth movements of the central nervous system and the cerebrospinal fluid spaces can be observed if we 3D model and 3D print these structures? So we're looking for what movements do we see. Second, is there evidence of Sutherland's motility? All these movements that were described in the works of Sutherland, which we'll get to soon, is there any evidence of this in the growth movements? And finally, can we find fulcra that these move around and show a nature of fluctuation? So basically, what are the movements? Do they match the motility described? And are there restraining functions that act as fulcrums? In my method, I had 7 specimens that worked from the MRIs previously mentioned. Carnegie ages 13 through 22. I 3D printed them at 12 times the size. I qualitatively analyzed the curvature. So I went through and I made large charts about what's the curvature, where, is it a strong curvature, is it a weak curvature, and how does it change? Important to remember that all statements are relative. If I say something lengthens in the longitudinal plane, it's because, or longitudinal direction, it's because it lengthens in relation to the transverse dimension, for instance. And because I was modeling the nervous system, there's a bias towards nervous tissue as a fulcrum. Blechschmidt talks about all sorts of other tissues, ligamentous tissues or arteries that may provide these kind of fulcrums, but because I was modeling the nervous system, that's what showed up the most strongly. And this is the 3D printed models that I made. On the top in blue are the ventricles, and on the bottom in yellow are the central nervous system. These are great fun, and they really help you see the changes in the nervous system. I use them as a kind of feedback loop. I would think of something, I would think about how it worked, and then I would look at the model and it would say, yes, this is accurate, no, it's not. I would be able to track the landmarks to really see if what I thought was moving was actually moving. And I used it to challenge my internal models and ideas. So here we will start with the rhombencephalon, also known as the hindbrain, creating such structures as the pons, the brainstem, and the cerebellum. Now, we see one very, very strong movement here, and that is the folding of the pontine flexure. This is the pontine flexure right here, and we can see that it increases with each progressive stage. We can also see that it starts as a very longitudinal structure and ends up as a very transverse structure. And that is the definition given by Sutherland for the inhalation phase. So we can name this fourth ventricle by this parameter in the inhalation phase. We can also see that there's compression happening here. And that compression looks kind of like someone squeezing bellows, which is an image Sutherland actually used for the fourth ventricle and the cerebellum. Finally, in the time where things are being squeezed like bellows, it's creating pressure. And interestingly enough, we see this is a high pressure area in the postnatal life, especially in the adult. I'll also bring your attention to this structure right here, which is the trigeminal ganglion. This is the main fulcrum I found for this area. This is restraining the front of the pontine flexure, which then allows everything to move away from it and do this folding. So cranial nerves 6 and 7 also seemed involved, but cranial nerve number 5 is the most important, I think. Next, in the rhombencephalon, we have this wrapping around. Now, this is a movement I would have missed if I hadn't been really looking at the landmarks, which to an outside observer might look clear, but wasn't at the beginning. So you can see these dots are at the same landmark each time. You can see the angles that I was able to follow and how they really wrap around. Now, if you join your hands like this, and you open them, and you close them, and then you put this in the same direction as these, this is the movement that Sutherland described for the rhombencephalon. And it's exactly what happens. He says when you open your elbows, it's the inhale. And you can see that this is the opening of the elbows inhale, which happens right here. And although I think all the other cranial nerves previously mentioned do play a role in this, I think that the vestibulocochlear, which we will see later, is the most present because we see this very strong angle in it. As the last part of the change from a longitudinal to a transverse structure in the rhombencephalon, we'll look at the movement, superior movement of the rhombic lips. Now we can see that it starts out at this angle, gets kind of flatter, and then even points upward at the end. And one of Sutherland's students, Schooley, described this movement of the cerebellum, which then pushes on the tent, the tentorium cerebelli, moving things into an inhalation phase. So we have another strong indication of inhalation. Now the question for the fulcrum is very interesting because we can see this is a very thin area in relation to everything else. And here we see cranial nerve 4, the trochlear nerve, the only one that emerges from the posterior of the neural tube. And what it appears as this goes to the eyes is that this is restraining this area and allowing everything to move past it. So again, things are moving around the trochlear nerve, which seems to create a cycle. Next, we move on to the third ventricle. This is seen from what I call anterior. In the adult, it's actually kind of seen from the viewpoint of the rhombencephalon. So here we have the opposite movement. Here we have the transverse diameter. Here we have the longitudinal dimension. And we can see that the transverse diameter really does not increase, but longitudinally it keeps getting longer and longer. This follows Sutherland's speaking that there's a V of this structure that narrows. And in addition to the general idea of the longitudinal increase of the neural tube. So we have this as an exhalation movement as opposed to the previous inhalation movement of the rhombencephalon. So the question is, why is there a strong longitudinal increase going from here all the way to this longitudinal increase and very little transverse increase? The reason I found is shown in the cranial nerve paths that I've overlaid across the ventricle here. You can see this is a very thin area of the ventricle. And what happens is it's not that the brain tissue doesn't increase in thickness. It just grows slowly outwards, but also grows in towards the ventricle itself. And we can see this especially right here and right here, where these areas are getting even obliterated in the middle. And we can see that the reason it gets squished here is actually because of the hemisphere. The rapidly growing hemisphere, in addition to the cranial nerves, keeps everything nice and thin. This also looks like a place of heavy compression, and interestingly enough, there are high rates of flow and acceleration in the third ventricle. It's also the most regular of the ventricles when seen in studies. This is another image of the third ventricle right here and the brain on the outside. And I just wanted to bring your attention to the fact that although there is some effect visible of the hemisphere up here and the cranial nerves down here, there's even greater effect on the area of the ventricle. So this suggests that there's a really strong growth in towards the ventricle and not just a slowing of growth externally. The next structure I'll discuss is the pituitary. Now, this right here is the pituitary in formation. This is the notochord, and this is the future mouth, just to situate you. Now, it's important to notice that the pituitary in all of these is very stable, similar to the trigeminal ganglion, which we saw before. It always sticks right between these trigeminal ganglion the whole time. Now, the tip of the notochord has been noted both by Sutherland and by Bletchman as being a very stable area, an area that's kind of central. And it's very interesting to see how that stable area at the tip of the notochord seems to exercise this ligamentous pull on the pituitary gland. Now, in terms of Sutherland gave the descent of the pituitary as a exhalation movement. Now here we don't see exactly that the pituitary extends, but we see the pituitary stay in the same spot while the posterior aspect of the central nervous system grows and grows. This happens, according to Bletchman, just because there's thin tissue that's easy to grow, easy to stretch right here. In the front, there's all sorts of crowded, there's the face, there's the mouth, there's the developing gut. All this is in the front, the eyes. And so we can see this rapid growth backwards, away, which I place as an exhalation movement. Continuing on the rapid expansion on the posterior side of the brain, we come to the hemispheres. Now in the hemispheres, we see that there's a strong longitudinal increase and not a strong transverse increase, putting it squarely in the exhalation phase. The other thing that puts it in the exhalation phase is the description Sutherland used of the coiling of the hemispheres. Now, we can see that this is coiling right here. It's moving around something. And interestingly enough, this coiling of the ram's horns is often called. It strikes me as feeling like the point is coiling around. And we can see it kind of is. But if we look at the relationship of the landmarks between this orange line and the green dot, we can see that the green dot really slowly approaches the orange line in relation to this red dot for the occipital area, really shooting backwards and gaining a lot of ground. So we see this is actually, it is like a coiling right there, and it coils around the insula. And this coiling around the insula is the reflection or the original gyri and sulcus. So we have the gyri and the sulcus. This would be the bottom, this would be the gyri. If we continue from there, we can see that Sutherland described the gyres as becoming less defined during inhalation and more defined during exhalation. So this is another sign of exhalation right here that matches Sutherland's writings. Insula being the fulcrum. We continue our look at the hemispheres by looking at the lateral ventricles. Here we see that as this strong posterior expansion happens, the insula grows in, and it also reaches forward, or what I would call superior. And in addition, creates a new indentation here. And if we look at it, it looks like there's a rotation around this point. Now that point, this area, is the foramen of Monroe, and it is what Sutherland described as the fulcrum of rotation for the lateral ventricles. So here we see it on the sagittal plane. We can also see it on the in the frontal plane. This is a line I placed on a ridge to track, and we can see that it's on the lateral side here, and that this is flat where the arrow is. And in the next stage, it is rolled over and is on the anterior side, and that flat surface has actually even buckled. So it's rolling over like this. So instead of this idea that everything is expanding just like a balloon, just in all directions, these restraining functions here cause a rolling motion around the foramen of Monroe. This is actually where the choroid plexus enters in, and was something that was said by Sutherland. Another interesting thing is that this is not an area of compression. This is an area that seems billowy to me. And in postnatal life, it is not an area of high CSF flow. It is a low area CSF flow. So now we can bring it all together. If we look at first the rhombencephalon, we can see that it increases transversely in the orange and blue arrows and decreases longitudinally as the pontine flexure squishes from the pink and the white arrows, and we have a strong inhalation movement. The diencephalon is lengthening longitudinally, the pituitary is descending, and it is not increasing transversely. So we have an exhalation movement. The hemisphere is increasing longitudinally, more than it is increasing transversely. And we have this coiling movement, all exhalation movements. So that was the very interesting finding, was that we have a fluctuation inside the brain of the developing embryo, according to these parameters of Sutherland. We have inhalation and an exhalation, and in the middle it's a little bit confused in the mesencephalon. I don't have time to go into the mesencephalon, but it's an interesting bridge. So that's fascinating. Now the other fascinating thing is that if we look at the red and the pink arrows, this is the area of the cranial base, and so this is creating an overall extension of the cranial base, even though there's two different phases happening inside the embryonic brain. And this adds a lot of complexity, and it makes you think like, oh, well, even if there's an exhalation of the cranial base, what's happening inside the container of the cranium? And so yeah, you have a peak and trough inside. Now, for real fluctuation, you would have to have a reversal of the structures. You would have to have inhalation become exhalation and exhalation become inhalation. And we can see that in two places. The first is in a stage that I did not model. It's Carnegie stage 11. And we can see that although in the stages we were looking at, there's an exhalation of the prosencephalon and diencephalon. Here, there's an inhalation shown by the increase in transverse diameter and actually the flexion of the cranial base as opposed to the extension that we saw in the later phases. This is the area of the future rhombencephalon, and we can see that there's a decrease in the transverse diameter. So for me, this shows that these are being reversed in the next stage, and this shows to me a fluctuation. We can also see this as a partially in the Carnegie stage 22 embryo, which I did model. Now, interesting in the Carnegie stage 22 is that the rhombencephalon actually centrally, not laterally, but centrally starts to elongate. It starts to almost unfold. The pontine flexure gets actually less intense, and that is a movement of exhalation. So we go from inhalation to exhalation. These structures of the rhombencephalon and diencephalon are very, very connected by a lot of cranial nerves and tissue and all sorts of stuff. So interestingly, the diencephalon kind of follows suit, and it also reverses, and we're actually getting more of a flexion of this cranial base right here. Flexion between here and here. The hemispheres have a whole power to themselves. It's like there's the lateral structures, just like here. They haven't gotten the message, and they are continuing in their exhalation pattern. And the real interesting thing here is that this meeting of forces seems to cause a buckling right here. This buckling right here, this is moving that way, this is not moving because it's getting pushed by the hemispheres, and so there's a buckling right here. And this area of buckling is the future pituitary. So it's nice that, actually I didn't answer my question about the pituitary originally with Sutherland, but I got a new version of the question of what's happening with these opposing forces at this moment. And the question is there something which is causing this buckling to be able to happen? And my response is that this is where the buckling is happening, and this is the third cranial nerve, right on the other side of this buckling. So again, we get a fold on the opposite side of the cranial nerve, number 3, which also kind of acts as a resistance factor for the diencephalon, keeping the third ventricle thin. Just like we have the trigeminal here, which is folding the rhombencephalon, just like we have cranial nerve number 8, the vestibulocochlear, which is causing the rhombencephalon to swing around in the back. Just like we have cranial nerve 4, which is inhibiting this area of the isthmus and creating the delineation between the mesencephalon and the rhombencephalon and letting the rhombic lips rise. So it all seems to work out quite nicely. Here you have a little recap of what the vesicle is, what the movement is doing, and what I found as the restraining function. So, a little bit of osteopathic relevance. First off, read your Sutherland. It's fascinating and can lead you to some very interesting methods of thought. But just like I was just discussing, importance of cranial nerves. So this brings us to think, how can the cranial movement be restrained just because the cranial nerve is restrained? And maybe the cranial nerve is restrained because the structure it innervates is restrained. So it brings a connection between, you know, the face, even the gut system, and the brain in cranial work. Also, this balance between mobility and restraint. In osteopathy, we're always trying to add mobility, but add mobility in relation to what? How can we restore the fulcrums, and how can we find where the good fulcrum is? This is a big question, I think, and very interesting to see this in light of the cranial nerves. And one final one, although there are many to think about, is the idea of entering into complexity. So when I found that there is a fluctuation inside the cranium in these growth patterns, and that on the outside it's an exhalation movement or an extension movement of the cranial base, this makes me think, oh, I always need to look underneath to see how the balance is inside. And that's a balance. There's a balance inside the balance, or inside the fluctuation. So that was very interesting, and I think this idea of balancing of polarities might be related to the idea of potency that Sutherland talked about, and I did not enter into. So in conclusion, Sutherland's motility was found in opposing phases, showing evidence of fluctuation. The cranial nerves provide a resistance leading to differentiation, and the growth movements also give a characteristic to the ventricles. Here are some references. Some thank you to Brian Freeman, whose DVDs on embryology really inspired me to do this work. He keeps saying, like, and you can do this too. You don't have to be in an embryology lab, and you're right. Thank you, Bradley Smith, for providing the embryo MRIs. Thank you, Julia Fetisson, for being such an awesome thesis advisor, recommended for anybody. Thank you to the jury. This is a recording after the jury. I didn't get that recording, so thanks for being my jury anyway. And if you have any questions, you can let me know. bonesbreathing@gmail.com. I should write that here. And in case anybody was wondering why it took a couple months to make this recording, when it was fresh in my brain before, it's because my brain was fried and I had to go sailing on this boat.